China just invented paint that generates electricity when it rains, and laboratories in 3 other countries are already scrambling to catch up. In early testing, a coated wall the size of a single garage door kept a string of outdoor lights running through an entire storm without touching the grid. You heard that right. Roughly the power draw of a small refrigerator, pulled straight out of falling water. And that is just the beginning. The race is not really about paint at all. It is about who controls the next quiet source of power for a warming, storm-heavy planet. This storm just became a resource. Hit a quick like and subscribe so you don't miss the next one. By the end of this video, you will understand exactly why so many engineers are suddenly obsessed with wet walls. Every other country building solar panels, just watch the weather itself become competition. To understand why this paint matters, you first have to understand what it is quietly replacing. And that technology earned its place the hard way. Solar power did not win by accident. It won because the physics were simple, the manufacturing scaled, and the economics eventually became impossible to argue with. Engineers love solar because a photovoltaic cell has almost no moving parts to break down over 20 years of weather. Manufacturers love solar because a panel built in one factory works identically, whether it ships to Arizona or Andalusia. Governments love solar because the cost of a single watt of solar capacity has fallen more than 90% since 2010. Picture a technology that once cost as much as a small car per household, now costing less than a decent bicycle. That collapse in price is not a footnote. It is the single biggest reason renewable energy stopped being a moral choice and became a financial one. Here is what makes this incredibly exciting to any engineer who has studied it. Solar did all of this while depending on one condition it cannot control. It needs direct sunlight, the same way a battery needs a working circuit. Remove the input, and the brilliant design underneath does nothing at all. And yet, for 15 years, the industry treated cloudy skies and rainstorms as simple downtime, a gap in production to be smoothed over with batteries and grid backup rather than a problem worth solving directly. So why didn't anyone solve this sooner? Partly because the obvious fixes, bigger batteries, more storage, worked well enough to make the harder question feel unnecessary. Partly because nobody had a serious reason to believe a rainstorm could be treated as fuel rather than an inconvenience. That assumption was reasonable. Rain is chaotic, low energy, and diffuse. Nothing like the steady, concentrated push of sunlight hitting a fixed panel at a fixed angle. Extracting meaningful electricity from something as random as falling water sounded, to most working engineers, like trying to power a city from the sound of applause. The instinct to dismiss it was not laziness. It was informed skepticism, earned by decades of failed attempts at exotic energy harvesting that never left the lab. Solar panels turned sunlight into one of the cheapest forms of power humanity has ever built. But somewhere in a materials lab, a group of researchers started asking a much stranger question. What if the rain itself was not the problem, but the missing half of the system? The flaw in solar power is not a defect. It is baked into the physics, and it has been sitting in plain sight the entire time. A standard rooftop system loses somewhere between 10 and 25% of its annual output to cloud cover and rain, depending on the region. In a place like southern China during monsoon season, that gap can stretch across nearly 4 full months a year, roughly the length of an entire school semester with the lights dimmed. This is not about solar being a bad technology. It is about solar being an incomplete one, built to capture exactly one kind of weather and nothing else. Quantify that further, and the picture gets sharper. Global solar capacity now exceeds 1.6 terawatts installed worldwide, enough to power more than 1 billion homes on a clear day. Yet weather-related downtime costs the solar industry an estimated $45 billion a year in lost generation and backup infrastructure, roughly the entire annual budget of a mid-sized country, spent compensating for weather the panels simply cannot use. Here is the detail that puts everything into perspective. Rain does not just fail to help solar panels. In heavy storms, it actively shuts them down, since the same clouds blocking the sun are usually the ones producing the rain in the first place. The consequence is not abstract. It shows up as grid instability during storm season, as utilities forced to keep fossil fuel plants idling on standby for the exact days renewable output collapses, and as higher electricity costs pass down to anyone paying a monthly bill. In coastal manufacturing hubs, factories that rely on rooftop solar to offset peak hour rates often watch that savings evaporate for days at a time whenever a typhoon system moves through. Every rainy day is, in a very literal sense, a day the sun's investment sits idle while the storm outside goes entirely to waste, a resource pouring down onto exactly the panels built to ignore it. For years, the working theory was simple. Build more batteries, build a smarter grid, and treat the rain as something to be endured rather than used. Researchers had noticed almost in passing that raindrops carry a small electrical charge as they fall and strike a surface, a curiosity mentioned in physics papers for decades, filed away as too weak to matter. In 2020, a material science team in eastern China began answering that question with data that was harder to dismiss than anything the field had seen before. The team behind this breakthrough came out of Suzhou University, working alongside materials engineers at the Chinese Academy of Sciences in Beijing. And they did not set out to reinvent solar power. They set out to answer a much smaller question. What actually happens at the molecular level in the instant a raindrop touches the surface? The core idea sounds almost too simple once you hear it. Every time two different materials touch and separate, electrons shuffle between them, leaving one surface slightly positive and the other slightly negative. The same effect that makes a sock cling to a sweater fresh out of the dryer. Earlier attempts to harvest this effect from rainfall had failed for a specific, well-documented reason. Older prototypes used metal electrodes exposed directly to water, and standing moisture on bare metal caused corrosion within weeks, along with electrical shorting that killed output almost as fast as it was generated. Teams in Japan and the Netherlands had tried variations on this same approach through the early 2010s, and each version ran into the identical wall. Water is an excellent conductor, which sounds useful right up until it starts short-circuiting the very components meant to capture its charge. Here is the part that actually explains the leap. The fix was not a stronger electrode. It was hiding the electrode entirely behind a microscopically thin polymer skin, the way a raincoat keeps you dry without needing to touch the rain at all. That polymer layer, roughly 1,000 times thinner than a human hair, is the entire innovation. It lets the raindrop's electrical charge transfer through by induction rather than direct contact, meaning the metal underneath never actually gets wet. Picture a window pane that lets sound through but keeps out the rain. And that is functionally what this coating does with electric charge instead of sound. Each droplet that lands and rolls off the surface completes a tiny circuit, transferring a pulse of current before the next drop arrives to repeat the process. What changed is not the physics of the raindrop. What changed is the engineering underneath it, built to survive contact with water indefinitely instead of failing after a handful of storms. Previous coatings degraded after roughly 200 hours of exposure. This one, according to lab testing, held stable output past 6,000 hours, the rough equivalent of 2 full years of regional rainfall compressed into a single accelerated test. The chemistry finally worked. The question was whether it could survive outside a laboratory. Here is the number that matters most, and it needs to be said plainly before anything else. This coating is nowhere close to replacing solar panels as a primary power source. Peak output sits around 0.12 watts per square meter during heavy rainfall, compared to roughly 200 watts per square meter from a standard solar panel under full midday sun. On paper, that gap looks disqualifying. But here is what that number actually means in practice. Solar panels produce essentially nothing during a storm, meaning the honest comparison is not paint versus panel. It is a small trickle of power versus the complete absence of any power at all. Anchor that gap against how most people would actually use it. A single coated exterior wall on a small building will not run a refrigerator or charge an electric car. It can, comfortably, keep a bank of environmental sensors running, trickle charge a backup battery for emergency lighting, or power a low-draw security camera through an entire multi-day storm without any grid connection whatsoever. For the applications that matter, remote monitoring stations, disaster response equipment, and off-grid infrastructure, that is not a limitation. That is the entire point. Here is what most people get wrong about this technology. They judge it by solar's job description instead of its own. The unexpected advantage shows up specifically where solar fails hardest. During a typhoon, when solar output can drop to zero for 72 consecutive hours, a rain harvesting coating hits its performance peak. At the exact moment the grid is most likely to be unreliable. Not a replacement for solar, not a redundant backup, not a novelty. And it is a second power source engineered to activate precisely when the first one goes dark. One non-obvious application already in testing: coastal flood monitoring buoys along China's southeastern shoreline, where swapping batteries by boat during a storm is expensive and occasionally dangerous. Engineers noted that a single maintenance trip by boat can cost more than the sensor itself. So removing the need for that trip entirely changes the economics of the whole monitoring network. A self-powered coating solves a logistics problem as much as an energy one. And in remote deployments, logistics is usually the more expensive half of the equation. The same logic applies to agricultural sensors scattered across rice paddies during the wet season, where running new wiring across flooded fields is often more costly than the sensors themselves. The question was no longer whether the coating worked. The question was whether it could survive a real coastline, not a controlled lab chamber built to be forgiving. In the summer of 2023, engineers coated a stretch of exterior wall on a research building in Suzhou, roughly the size of 2 highway billboards placed side by side, and left it running through an entire monsoon season with no human intervention. Over 4 months of recorded rainfall, the coating delivered a steady average output that matched laboratory projections within 6%, a level of accuracy field engineers rarely see on a first full-scale deployment. The field matched the forecast. In an industry full of technologies that look extraordinary in a climate-controlled lab and then quietly underperform outdoors, that kind of agreement between prediction and reality is what actually earns trust from the people who have to sign off on funding the next stage. Field validation matters more here than almost anywhere else in material science, because lab rain is clean, filtered, and falls at a controlled angle. Real rain carries dust, pollution particles, and wildly inconsistent droplet sizes that can foul a delicate coating within days. This one did not foul. Researchers attribute that resilience to the same thin polymer skin that protects the electrode, which turned out to double as a barrier against grit and airborne particulate buildup. The coating was also engineered to bond with standard exterior primer, already used across Chinese construction sites, meaning builders do not need a new application process or specialized equipment. It goes on with the same sprayers already sitting in every contractor's truck, applied in a single afternoon by a 2-person crew. We were not trying to build a new power plant, one senior researcher on the project explained. If you are the kind of person who finds a raindrop turning into usable current genuinely surprising, the next part is going to be even harder to believe, and hit subscribe so you are there when we cover it. All 4 months of performance data from the Suzhou test site were published to an open academic repository, available for any research team in the world to independently verify or challenge, down to the hourly rainfall readings used to generate each figure. It started with one application where cost and simplicity mattered more than raw output. Then it spread outward from there, first to weather stations, then to flood buoys, then to entire coastal monitoring networks stretching across 3 provinces. The claim now had receipts. More than 140 international patent families now cite this rain harvesting approach or a close variation of it. These are not academic citations. These are legal and financial commitments, the kind companies only file when they believe a technology is worth defending in court a decade from now. A Shenzhen-based electronics manufacturer announced in early 2024 a pilot order to coat rooftop sensor arrays across 400 logistics warehouses, citing projected maintenance savings of roughly $2 million over 5 years. A European engineering firm based in the Netherlands, long focused on flood monitoring infrastructure, signed a licensing agreement the same year to integrate the coating into next-generation river gauges across the Rhine Delta. Not a curiosity, not a lab demo, not a press release with nothing behind it. It is a supply chain decision being made by companies that do not spend money on technologies they consider unproven. China's Ministry of Science and Technology has also listed self-powered environmental sensing as a priority research category in its most recent 5-year technology roadmap, a regulatory signal that tends to unlock additional public funding for exactly this kind of applied materials work. Here is the detail that puts the corporate math into perspective. For any coastal monitoring network operator, a sensor that never needs a battery swap by boat is not a nice-to-have. It is a direct line item removed from an annual maintenance budget. In any market where labor and logistics cost more than the hardware itself, a 90% reduction in maintenance visits is not a trend. It is a competitive pressure no serious operator can afford to ignore. A Japanese materials conglomerate confirmed in 2024 that it was independently testing a similar coating chemistry for use on offshore wind turbine housings, where corrosion monitoring in wet conditions has historically required expensive manual inspection. And here is the part that surprised even people inside the industry. A South Korean smart city consortium began evaluating the coating not for its power output at all, but simply as a self-diagnosing rain sensor, since the electrical signal itself changes shape depending on rainfall intensity, offering weather data as a free byproduct of the power it generates. The full performance data set behind these commercial pilots remains published on the same open academic repository referenced by the original Suzhou trial, allowing outside engineers to check the manufacturer's claims against the underlying numbers themselves. The lab result had become a line item on corporate balance sheets, and that shift changes everything about how fast this technology moves next. Researchers estimate that if this coating were applied across just 10% of viable exterior surfaces in China's most rain-heavy provinces, it could offset the storm season energy gap for roughly 12 million off-grid or backup-dependent sensors and small devices, a number close to the entire population of a country like Belgium, running on power that used to just wash down a drainpipe. Beyond raw output, there is a secondary benefit worth naming directly. Removing an estimated 800,000 battery replacements a year from remote monitoring networks, cutting both the manufacturing emissions tied to disposable batteries and the diesel-fueled boat and helicopter trips currently used to service them. Fewer discarded lithium cells also means less strain on the mining and recycling systems already struggling to keep pace with global battery demand. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. First, output remains extremely low, relative to almost any other power source, meaning this will never scale to residential electricity generation the way solar has. Second, durability testing beyond 6,000 accelerated hours still has not been matched by a full decade of real-world weathering, and materials that look stable in year 1 sometimes degrade unpredictably by year 8. Third, manufacturing the polymer layer at a consistent nanometer scale thickness across large surfaces remains expensive at anything beyond small pilot batches. Fourth, regulatory approval for construction-grade coatings varies enormously by country, and China's fast-moving standards process does not automatically translate to approval in the European Union or the United States. Fifth, this technology has essentially no track record in freezing climates, where ice formation could change the entire surface, chemistry the coating depends on. Sixth, cost per square meter at current pilot scale production still runs several times higher than standard exterior paint, a gap that only closes with manufacturing volume nobody has reached yet. Here is the part that keeps engineers honest. A coating that performs beautifully in Suzhou humidity has not yet proven it can survive a Minnesota winter. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as a chemistry one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the climate demands is a different question entirely. The story of electricity generating paint is ultimately the story of what human civilization can build and where it can build it. For most of industrial history, useful power required infrastructure, wires, poles, substations, fuel deliveries, which meant the places with the least infrastructure were also the places left furthest behind. A coating that turns an existing wall into a power source does not need any of that. It needs a wall and a storm, both of which already exist in exactly the places that need power the most. That is where the equity question becomes impossible to ignore. Rural monitoring stations across Southeast Asia, flood-prone river deltas in Bangladesh, and off-grid villages scattered through the Philippine archipelago all share the same problem: heavy annual rainfall paired with unreliable or non-existent electrical infrastructure. Right now, that access gap is real, and this technology has been tested almost exclusively in controlled Chinese facilities, meaning genuinely low-cost, low-maintenance deployment in the places that need it most is still years away rather than months. What is genuinely new here, not incrementally better, but categorically different, is treating weather itself as an energy input rather than an interruption to one. That is not a minor improvement. It is a different category of solution, one that stops asking how to store around bad weather and starts asking how to use it directly. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed climate-vulnerable regions actually need is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. Small numbers, multiplied across enough surfaces and enough storms, compound the same way interest does in a bank account, quietly, and then all at once, until an entire category of infrastructure looks different than it did a decade earlier. If a wall that generates power from rain raises the question of what else in a building might be hiding untapped potential, that story is worth understanding too, and it is the subject of our next video. China's new material just replaced wood forever. The link is in the description. If this changed how you think about the surfaces around you, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every week. Now I want to hear from you in the comments. Is a technology this far from replacing solar worth this much excitement? Or is China simply chasing headlines faster than the physics can actually deliver?